All right, we've got a system of 3 linear congruences, and we're going to use our ideas from the Chinese remainder theorem to help us solve it. So we know that in the end, our solution will have the form x equal to some initial value mod 5 times 7 times 11. So that's going to be initial value mod 385. Okay, so I know this, but I'm going to start looking just at my first 2 equations. So by inspection of the first 2 equations, and I'm using inspection because it's nice and easy for these 2. So I know from the first one I've got 2 potential solutions are 2, 7, 12, 17, etc. In the second equation, I have 3, 10, 17. I'm stopping there because I see 17 and 17. So from this system, I know that x is going to be equal to 17 plus 35k. And I know that because of my 5 and my 7. All right, now I have also my third equation for mod 11. So I'm using now the solution of these incorporated with this one to solve. Well, this one is not so easy to do by inspection because these numbers are going to get really big and ugly really fast. And 4 mod 11 isn't any nicer. But I know that 4 mod 11 is also equal to 4 plus 11. Let's use another variable. Let's call it p. And of course, k and p are integers. So now, based on these 2, I can connect back to my idea of linear Diophantine equations and solve that. So both of these are x. That implies 17 plus 35k is equal to 4 plus 11p. And knowing that k and p are integers is what makes this Diophantine a Diophantine equation. So putting these together, I'm going to have that 35k minus 11p is going to be equal to negative 13. All right. So now I want to end up looking for, to know that it has a solution, I need to check that GCD of 35 and 11 is 1. That's true, so we have a solution. I can start looking at solving this to find my GCD. So I know that 35 is 11 times 3 plus 2. 11 is 2 times 5 plus 1. And then here is going to be my remainder. I know that my next line is going to end up giving me a 0 because I would have that my 2 is equal to 1 times 2 plus 0. So straight from here, this leads me to say that 1 is 11 minus 2 times 5. Instead of 2, I'm going to use this. My 2 is equal to 35 minus 11 times 3. And this is a multiplication symbol here. All right, so simplifying that, I can say that 1 is equal to, let's see, that's going to be 4 times 11 minus 5 times 35. Okay, I know that this is going to be equal to 1, but what I want it to be equal to is negative 13. So I'm going to multiply everything by negative 13. So 4 times negative 13 times 11 minus 5 times negative 13 times 35. Simplifying this, that's going to give me 65 minus 4 times negative 13. Something seems to be wrong here with my 4, and it's because I didn't distribute my 5. So negative 5 times negative 3 should have been positive 15 plus 1 is 16. So let's go in and make that 16. All right, and then down here I would have 16. No, that's still 13. My 4 is 16. So 16 times negative 13 is negative 208 times 11, and that gives me my negative 13. This implies then from this equation up here, k is equal to 65, and my p-value is 208. Using either one of those, I can substitute into my initial equation up here. So if I look at my x value, then x was equal to 17 plus 35 times the k value. So if I expand that, then I would get 2,292. So there's one solution, but of course that value is not within my mod of 385. So converting this, so I've got one general solution is 2,292, but I could also convert 2,292 mod 385, and that's going to end up giving me 367 mod 385. So then I could define my very initial positive solution as 367. And then all values of x, I could say, are going to be equal to 367 plus 385, and I'm going to use yet another variable t, where t is some sort of integer. Okay. So if we're looking only for our positive solutions, then we would say positive integers, or we would say integers greater than 0, because we would want to start with 367 for positive solutions of x.